Okay, so we're going to start with number 1 here, and obviously the first thing I need to do is identify what the given information is and what's unknown. 4.2 meters per second at 245 is the mouse relative to the ship, so that's VAB. 13 meters per second at 81 degrees is the ship relative to the sea, so that's VC. And I remind myself that VAB, when added as a vector to VBC, will give me the resultant VAC, and that's exactly what's wanted. The mouse relative to the sea, which is VAC, is the unknown here, so my unknown is already isolated, and so now I just have to draw vector AB and add it to vector BC, and that will give me AC. So drawing vector AB, I'm going to be careful to keep it approximately to scale. It's going to be about 1/3 the size of BC, and I'm going to start off at 245 degrees, which is in the 3rd quadrant and a little bit closer to due south. So I'll draw like this. That's a 25-degree angle, and it's 4.2. And then I'm going to add to that, so I start from where I ended, add to that 13 meters per second at 81 degrees. It's going to be something like that, where I could draw this angle down here, but just to make my drawing easier to follow, I'm going to put it up here so that I can see the resultant is going to be from where I started to where I ended, and that of course is VAC. So now returning back to these original vectors, I'm going to do these solutions a couple of different ways. The first one, I'm going to show you making right triangles and just using right triangle trig. So if I make this vector, break it down into its components, there is a horizontal and vertical component. The horizontal can be found by sine of 25 is this horizontal component over 4.2, which when I solve for that I get 1.77. And of course this side is cosine of 25 is this side over 4.2, which gives me a value of 3.8. Then I'm going to do the same thing with the other vector that I added, break it down into horizontal and vertical components. And again, I could have done it down here. I'm just doing it up here just to keep out of the way of the vector I'm trying to find. And I didn't write this magnitude, it's 13. And so this side is going to be sine of 81 is this side over 13, which of course is 12.8. And obviously I didn't draw this very well to scale because the horizontal component is 2.0. Alright, so now I have everything I need to find the components of this resultant vector, which I've drawn in red here. You see this horizontal side is 2.0 up here minus 1.77. In other words, this was 2.0 to the right, and when I add 1.77 to the left and 2.0 to the right, I get 0.23 to the right. And so that's the horizontal component of the red vector. And then the vertical component, I went down 3.8 and up 12.8, giving me an up 9.0 when I subtract the 3.8 from the 12.8. So those are the two components of the vector that I was trying to find. I can do the Pythagorean theorem to find that the hypotenuse it basically ends up being about 9.0, I believe, because this is insignificant. And so my final answer, the speed at least, is 9.0 meters per second. And now all I need to do is identify this angle, which I can do using inverse tan of 9 over 0.23, and that gives me 88.5 degrees. So the velocity of the mouse relative to the sea, VAC, is 9.0 meters per second at 88.5 degrees. Alright, now problem 2, I'm going to work the exact same way. I know that 2.8 meters per second at 115 degrees is the mouse relative to the ship, so that's VAB. And once again, I've been given that the ship's velocity relative to the sea is 21 meters per second, so that's BC. And again, I've asked you to find VAC. Very straightforward, the exact same type of problem. I just have to be careful and add VAB and VBC correctly, and the resultant will be VAC. So I'm going to start off at 115 degrees, which is up here in the second quadrant. And so I could call that 2.8. And this angle then, since it's 115, that's my 25 degrees again. And then 21 meters per second at 152 is going to be a little closer to the horizontal, where that would be 28 degrees. And of course, again, I could have drawn this, should have drawn this much longer. Let me fix that. Because this is 21, and that's only 2.8. I probably should have used a straight edge there. At any rate, I'm going to break these down. Well, first of all, I'm going to show that VAC then is the vector sum of those two. And so now, again, I can break these down into their components by drawing right angles and then apply trig. This is going to be 2.5, this is going to be 1.2, and this is going to be 9.9, and the horizontal 19.7. So these are in the same direction this time. I have up and up will give me a total in the up direction of 12.4, and left gives me a total of 19.7 plus, oh, I apologize, this is not 19.7, this is 18.5, and added to 1.2 is my 19.7. Sorry about that. So then again, VAC is just the sum of these two components. It's 19.7 and 12.4. So I apply a Pythagorean theorem again. I get a velocity of 23.3 meters per second at, find this angle from tan, inverse tan of 12.4 over 19.7, and then it's touching the 180 degrees, but it's short of that, so I do 180 minus that angle will give me 148 degrees, I believe. Alright, then number 3. This time I've given you VAB, again, mouse, oh, excuse me, relative to the sea. So I've given you VAC there. And it's the ship is sailing relative to the sea, so that's VBC. And I've asked you for the mouse relative to the ship, so VAB. So this is the first time I've given you a bit of a curveball. I've asked you to take your VAB plus VBC equals VAC, but VAC is not unknown. VAB is, so I've got to subtract VBC from both sides. And so now I know that VAB is going to be VAC minus VBC. And you'll recall that if we subtract a vector, we add the opposite vector. So I need to draw VAC, but then I need to add to it not VBC, but the exact opposite of VBC. So if I start off with my 1.9 meters per second at 48 degrees, so I can draw 1.9 at 48 degrees. Then I'm going to add to it 19 meters per second at 304. Well, 304 would be down and to the right in the fourth quadrant, but the exact opposite I'm going to either add or subtract 180, whichever one keeps me within 0 to 360 degrees. And so I'm going to be at 124 degrees. So 124 degrees would be just 34 degrees past 90. And of course the magnitude of that is 19, which is much longer than this. I haven't quite drawn it to scale, but at least I've made it big enough that I can see that the resultant is going to be up and to the left. And that's the main thing, is just to make sure I know which direction the resultant is going to be. Otherwise I end up getting numbers that don't make sense. And so again, just going to break those down into their components. This 1.9 at 48 gives me a 1.3 horizontal and a 1.4 vertical. And the 19, when broken down, is a 15.8 and a 10.6. The horizontals are in the opposite directions, so I have to go 1.3 to the right and then 10.6 to the left. So that gives me a net in the horizontal direction of 9.3 to the left. The verticals are both up, so 1.4 up and 15.8 up when added together gives me 17.2 up. And so now Pythagorean theorem gives me 19.6 meters per second. And then again, inverse tan of 17.2 over 9.3 will give me this angle, and then this angle is touching 180, but it's not yet to 180, so I do 180 minus that angle, and that gives me 118 degrees. Alright, so now number 4 is a little bit different. I have given you this velocity, which is mass relative to ship. So I've given you everything you need to know about VAB. But then on ship relative to the sea, I've only given you the direction. So VAB, we know in its entirety, is 0.059 at 26 degrees. VBC, we don't know its speed, we know its direction is 81 degrees. And then I've given you VAC, mouse relative to C. I've given you everything you need to know about that, 2.1 at 87 degrees. So I could do this a couple of different ways. I could, since part of BC is unknown, I could isolate BC. The way I'm going to do it, though, is to go ahead and draw, because I know direction of BC, I just don't know its magnitude. I'm going to go ahead and draw it and just make it, some arbitrary length that I think looks reasonable to give me an AC of 2.1. And so I draw the the AB at 26 degrees, and it's 0.059, and then I add to that at an 81 degree angle some velocity v. So again, I know the direction's 81, I'm just going to call the speed v, but I know that that plus that, the sum, has to be 2.1 at an angle, and once again, like in the previous problem, I could draw this 87 here, but I'm going to draw it up here just to keep clear of the v that I'm trying to solve. You guys do understand, right? Because this is horizontal, this is 0 degrees, and so it's 81 degrees relative to 0. If I come up here, this is also horizontal, so these two horizontal lines are parallel, and so 81 here has to be, 87 here has to be 87 there. It's alternate interior angles, I think is the term. Anyways, so that's V. So now I just do what I've been doing, resolve these guys into components. This will be 0.053, and this will be 0.026. And the red vector, which was the resultant, VAC, can be broken down into 2.097 and 0.11. Well then, the unknown vector is these components. This side is 0.11, and this much of it is 0.053. That means that this horizontal component must be 0.057, because 0.053 and 0.057 equal 0.11. And then vertically, 2.1 is this side, the 0.026, plus this side, which leaves this side to be 2.07. So now this V is Pythagorean theorem 0.057 and 2.07 gives me a value of 2.072 meters per second. And that's the speed of the ship relative to the sea. If I'd asked for the velocity, obviously it's easy because I gave you the direction was 81 degrees already. But 2.07 is all I asked for here. All right. Number 5, I've given you mouse relative to ship, so that's VAB. And then I've told you that mouse relative to sea, which is VAC, is 0.9 at 261. And I've asked for ship relative to sea, which is VBC. So once again, I know VAB, when added as a vector to VBC, will give me VAC. In this case, VBC is unknown, so I'm going to subtract VAB from both sides. So VBC is VAC plus the opposite vector of AB. So I draw VAC, and that is the 0.9 at 261. Which is going to be like this, with that angle being 9 degrees. And then I'm going to add to that the opposite vector of 155. Well, 155 would be this way, and I should have drawn this up here, but 155 would be this way, so the opposite is going to be down and right, where this angle would be, and let me just maybe draw this side over here. If I had done 155, this side would be 25 degrees, right, where this is the horizontal. So if I go the opposite direction, before I went up and left 25 degrees, now I'm going to go down and right 25 degrees. So that shows me that is 25. The other way, of course, I could do it would be to add 180 to 155 degrees, and that's going to give me 335 degrees, which is, of course, the exact same answer I've gotten here, because this is 25 below 360. And, of course, that magnitude is 1.2. And the resultant vector then will be this guy, and that's VBC, which is what we've been asked to find. So once again, break these down into components. And this is also 25 because of alternate interior angles. And so break those guys down. Well, we've got the 1.2 breaks down into 0.51 and 1.1, and the 0.9 can be broken down into 0.14 and 0.89. And so then this is 0.14 to the left and 1.1 to the right. Gives me 0.96 to the right, and 0.89 down and 0.51 down gives me 1.4 down. And so those two make up that resultant vector, which when I use Pythagorean theorem to find the resultant gives me 1.7 meters per second. And of course, again, inverse tan of 1.4 over 0.96 will give me this angle, and that angle is below 360, so 360 minus that angle gives me 304 degrees. Alright, now number 6. I've given you the ship relative to the shore, that's BC, and then the mouse is running relative to the shore, so that's VAC, and I'm looking for VAB. So again, I apply the same logic I did up here. if I know BC, but I don't know AB, then I'm going to subtract BC from both sides. So I know already that VAB is going to be VAC minus VBC. So I just draw VAC, which is 3.3 at 286. That's going to be down and to the right. Where this angle is how much past 270 it is, which is 16 degrees. And that's 3.3. And then I would be going up at a 40-degree angle, but I'm adding the opposite vector, and so I go down and left at a 40-degree angle. And I'm going 2.9, so almost as far as that one. So 2.9. And of course, again, this angle is the same as this angle would have been, which is given as 40 degrees. And so now, again, I can add those two vectors and I get the resultant that looks like that. Well, the two legs of the 3.3 are 3.17 and 0.91. The two legs of the 2.9 are 1.86 and 2.22. So I go to the right 0.91 and to the left 2.22. That's a difference of 1.31. And I go down 3.17 and down 1.86. That gives me a total of 5.03. Pythagorean theorem tells me that those two added together are 5.2 meters per second. And then this angle I can get from tan and add it to 180. And so 5.2 meters per second at 255 degrees is the final answer for that one. Alright, so now is the first time that I'm going to throw you a little bit of a curveball, and instead of just giving you the velocity, I'm going to make you find it. And so here I've given you a distance and a time, and I've got to think in terms of, well, what's this distance relative to? It's how the mouse is going to move relative to the ship. And so someone else sitting on the ship is going to see the mouse move 39 meters. And so this distance divided by this time will give me the velocity of the mouse relative to the ship, which is AB. And of course, when I do that, I get, what is that, 1.26 meters per second at 25 degrees is VAB. And then I've given you the ship is sailing 7.4 relative to the sea, so that's VBC. And then I ask you a question of time about a distance relative to the sea. Well, in order to answer how long it takes the mouse to go this distance relative to the sea, I need to know the velocity of the mouse relative to the sea. So I've got to find VAC, which you probably would have figured out because I gave you VAB and VBC. But always think about this, right? What's this distance relative to? All right, so first we're going to find what VAC is, and then we can use that to find a time, which is unknown, given a distance that's measured relative to the c of the mouse. All right, so let's add our vectors. We've got 1.26 at 25 is what we're going to do first. And so there's that 25-degree angle again, 1.26. And then I'm going to add to that my 7.4 at 61. So real big, 7.4 at 61 degrees. And so then VAC is going to be the resultant of those two. So now break them down into components once again. And that gives me legs of this one that are 1.14 and 0.53. Legs of this one that are 3.59 and 6.47. They're both in the same direction, right and up, so I just add, and that gives me an up of 7 and a right of 4.73. And so then now it just becomes Pythagorean theorem. to get a velocity of 8.45 meters per second. Now I could find the direction of this by identifying this angle, but because I've asked for time here, all I need really know is the speed. So I've got a distance and a speed. That's enough to give me time. So I apply that speed is distance divided by time, therefore time is distance divided by speed. So long as these two agree, I can do this. And so, well, what's the distance? 16, that's the distance of the mouse relative to the sea, divided by the velocity of the mouse relative to the sea, which is 8.45, will give me the correct answer, which in this case is 1.9 seconds. Alright. Now, we're done with this mouse, so we're going to get rid of it. It's going to jump overboard, and it's going to jump overboard a distance 34 meters from the shore. So this one's a little bit tricky, I suppose, because I've got a current flowing parallel to the shore. Well, I could draw a picture and figure this out, but I've asked for the best case scenario. In other words, the mouse doesn't know any physics. It's just going to swim in the direction it thinks the shore is. And so it's going to, if here's the shore and the current's going this way, it's going to aim this way, right? It's just going to swim for shore. Now, of course, it's not going to end up there. It's going to go at an angle like this and end up very different location than where it aimed. But we want best case scenario, and as you've learned before, if I'm trying to get from point A to point B in the shortest time, I just aim straight for it. Now, this river, or the current of the ocean, is going to move me down relative to the ground, but all I care about is getting through the water as fast as possible. And so that's why I've aimed straight across. And so I really don't even have to draw a picture for this. I know that he's got to cover 34 meters in the water, right? To go from here to here, wherever he does it, is 34 meters in the water. And it doesn't matter that he's traveling this way relative to the shore. And so I can just say, apply this guy again, that time is a distance divided by a velocity, where this time the distance is 34 meters relative to the water, because that's all he has to get across, and I know he's swimming 0.5 meters per second relative to the water, and so that will tell me that it's going to take him 68 seconds to get across. So it's a little tricky, but it's actually simpler than any of the other problems. Similar to number 9 here. The shark spots him and starts swimming right after him. Well, the mouse has a 124 meter head start, but we know the shark is swimming 3.2 meters per second relative to the sea. Alright, well, so if I know the shark is swimming 3.2 meters per second relative to the sea, let's say that the mouse is A and the shark is B. That means this is VBC. Well, I know from the previous question that the velocity of the mouse relative to the sea is 0.5. So what I'm really wanting to know, if it's going to catch the mouse, what I really want to know is how fast is the shark moving relative to the mouse? Or VAB. And so I know VAC is equal to VAB. Excuse me, I'm just getting my letters all screwed up. VAB plus VBC. Well, I'd love to know what VAB is so I can subtract VBC from both sides. Well, and it doesn't matter what direction VAB and VBC are in. I can just tell that they've got to be in opposite directions, right? Because the shark's swimming straight for the mouse. So if the mouse is 0.5 towards the shore and the shark is 3.2 towards the shore, then when I subtract them, I have to flip one of them around. Well, that gives me a resultant of what? 2.7, right? So I know that the mouse and the shark are moving 2.7 meters per second relative to each other. So the question is, if this is the distance between the mouse and the shark, and this is the velocity between the mouse and the shark, how long is that going to take? Distance divided by velocity is 124 divided by 2.7. That means it's going to take 46 seconds for the shark to end up in the same location as the mouse. Well, 46 seconds, it was going to take him 68 seconds to get to shore. And so yes, the shark catches it, and that's the end of our mouse.